Hi, welcome back to the channel. So in this video we are going to see about the sampling theorem in detail. First of all, sampling theorem is about conversion from continuous time signal to discrete time signal. So if you want to convert continuous time to discrete time signal, we have some conditions. So we'll see that conditions with the help of the sampling theorem. We can able to represent the signal, and we can able to reconstruct the signal with the help of sampling theorem for some conditions. For this, first initially we will be having the message signal. So we can observe here the message signal, which is in time domain, can be represented as like this time, and this is the message signal. And in the frequency domain, we can write this as m of omega m here right hand side plus, and it is minus. So this m of t. Then after that we'll take C of t. So C of t is this one, which is a train of pulses. It is 0, ts, 2ts, minus ts, minus 2ts. So C of t, the train of pulse is minus. Here you can got minus infinity. Here it is plus infinity. So delta of t n minus ts. So it is meaning is at t equal to n ts, where you can take n value 0, 1, 2, 3 like that. So that is what we have written the C of t. So we take m of t and C of t, and we will take the sampler, and it is nothing but multiplier. So how it is going to multiply? It is just like, look at this, S of t is m of t multiplied by C of t. So how we are going to get m of t and C of t is S of t equal to m of t multiplied by C of t. So now look at this. Same thing what we have taken here. This is the message envelope which we have considered here, and this train of samples, the samples are at 0, ts, 2ts, minus ts, minus 2ts, right? So this S of t is a product between message and the carrier. Now after this, we should write this is in time domain, we should write this in frequency domain, right? So how to draw this is, look at this, S of t is converting S of omega, where we have considered this message as omega m positive, and this is minus omega m. Similarly, we have the series. So for the next one, for this we have the next fd, and here it is the next fd. You can observe here, this is omega m, and this part is omega s minus omega m. So omega s minus omega m obviously greater than omega m. So omega s is greater than 2 times omega m. So this you can observe in this type of sampling, which is represented by separating this guard. This is the guard band between the two FD signals. So we call this as oversampling. Okay. Next, come to the critical sampling. In this case, you can observe this diagram. It is touching. For this condition, omega s minus omega m is omega m. So omega s is equal to 2 times omega m, right? So this is called as the signals are touching to each other in case of the sampling. So it is called as critical sampling. And with respect to that, we will speak here later. Then one more sampling is undersampling. In this undersampling, so here overlapping between these FD signals, we can see. Look at this overlapping. So omega s minus omega m is less than omega m. So omega s is less than 2 omega m. So this is a case of undersampling. So the signal can be able to represent with the help of this time domain and to convert it into FDM domain signals only if this is the condition, omega s greater than 2 omega m, and also omega s equals to 2 omega m. This is are the conditions. So here the nyquist rate is called as omega s equal to this. This is critical sampling. We will call it as omega s equal to 2 omega m as a nyquist rate. Where what is omega s? 2 pi fs, and it is 2 of what is omega m? 2 pi fm. So 2 pi will get cancelled. So fs you will get 2 times fm. So this is called as what? Nyquist rate, or you can call it as sampling frequency. If the sampling frequency, it should be equals to 2 times the message frequency. So what is Nyquist interval? The reciprocal of this, because we know that t is equals to 1 by f. We can call this as Nyquist interval. T is equal to 1 by s. that is 1 by fs, that is 1 by 2fm. So overall the sampling theorem is, if the sampling frequency fs should be greater than or equal to 2 times the message frequency. If this is the condition, you can observe, if it is greater, we will be having this oversampling, and if it is equal, we will be having critical sampling. For these two conditions, we can able to represent, as well as we can able to reconstruct our signal like this and like this in FD domain. But if it is less than, it is going to be overlapping. So this is the importance of sampling theorem. We can convert continuous time signal into a discrete time signal like this by considering a number of samples. So that is about the sampling theorem. Thank you. We will see in the next video.